welcome to the course on molecules in motion. So, we have covered quite a bit of how the molecules or ions move in solution. We have actually gone into the definitions or various expressions which is usually used when we are talking about ions or molecules in motion. Like we have talked about the various conductivities. To begin with, I will go through whatever we had done in last 2 classes, summarize them and put in some new expressions which you will otherwise find in some books, which I had not mentioned previously. So, conductance, when we talk about conductance, it is usually represented as the inverse of resistance for any solution. So, we have not used this expression of conductance in previous lectures. So, this is the first time we are introducing conductance in the form of G. Various books use various nomenclatures, but as such we have only talked about resistivity in the last class, and today we are going to introduce another term which is known as conductance, which is 1 by R. 1 by R means the unit is going to ohm inverse, and from the expression of the G, that is conductance, you can see that it is inversely proportional to the length, and hence if you have the length decreasing, then the G or the conductance of the cell is going to increase. There is another term conductivity which is used here, which is represented as Kappa. I would like to tell you from now onwards, we are going to be, whenever we are talking about conductivities of electrolyte, we are going to be generally talking about them in the coming few lectures. We will be doing number of derivations. We are not going to just confine to what the definition is. So, whenever we are talking about conductivity, we usually represent it by Kappa. Okay. It is also known as specific conductance, and whenever we are representing conductivity with Kappa, that means you have to understand that we are dealing with the specific conductance. We have talked about specific conductance, we have talked about equivalent conductance, we have talked about molar conductance in the last lectures and in detail, and how they are related. We have not even discussed how they are going to be applied when we are talking about something like molecules in motion in a liquid phase or liquid medium. We have just gone in to discuss the various forms of the various conductivities, and we have found out their expression, we have given their units. So, what we are going to be taking down from now onwards, we are not going to visit that again. We are going to take whatever we have done as definitions, and to begin with, whenever I am talking about conductivity, we are representing this specific conductance or Kappa. And in this expression of conductance, you can see it is going to be directly proportional to the area and inversely proportional to the length of the length between the two plates for a cell. So, conductivity, when we are talking about molecules in motion, understand we are talking about transport properties. We are transporting something through the liquid phase or liquid medium. Conductivity depends on the number of ions. Conductivity means, what does it mean? How it is going to something conducting means some charges moving from one place to another. Then we say it is conducting, right. When electrons are moving in a solid, we say the electron is the material is conducting when the electrons are flowing. Similarly, in the liquid system, when you have a medium as liquid, what you have, we talk in terms of conductivity, where ions are going to be the carriers of the charge across the solution system. So, this conductivity hence must depend on the number of ions which is associated with the system. So, whenever we talk about conductivity, henceforth we are going to be looking into the number of ions, and the only two things which we are going to be concentrating on: conductivity and molar conductivity. Conductivity means Kappa, which is represented as the specific conductance, and the molar conductivity as lambda. And in the previous classes we have seen that the molar conductivity is nothing but kappa by C. C is in moles per liter. Okay. So, before we go into the discussions of today's lecture, we will revisit few things which we had talked. I am emphasizing that we are not going to talk about any other forms of conductivity other than specific conductance or specific conductivity and molar conductivity. So, in the last class we had talked about what are the factors which affect the specific conductivity of a system. The factors that affect the specific conductivity of the system will obviously affect the transport of the charges through the solution system. So, we are now going to talk about, this is something which is already there in the last lecture. I am just taking this up so that it is going to be easier for us to move on further. So, if I talk about specific conductivity, that means I am talking about kappa. What are the factors which influence kappa in an electrolyte solution? What are the factors? Obviously, the nature of the solute and solvent, the concentration of free ions in the solution system or electrolyte solution, the mobility of the free ions in the solution system, and temperature. So, if you increase the temperature, what will happen? What will happen if the ions are freely moving? That means they are highly mobile, that mobility is high. And if the ions are the concentration of ions or free ions in the solution is large, what is going to happen? And what happens to the type of solvent system or the solute system you are dealing with? So, when we are talking about specific conductance, the number of ions and their mobility is something which is very defining. Specific conductance is majorly, if I have a system, I am carrying out an experiment, doing the experiment at room temperature, and if my solvent system is the same, I am using the same solvent, I can use water, I can use methanol, whatever the medium is. If my solution system is the same and the temperature is held constant, then the two factors which will be determining the specific conductivity of a substance is going to be the number of free ions which is generated and how they are moving, how freely they are moving in the electrolyte solution. So, what happens, how does these two affect the specific conductance value, kappa value? More is the concentration of the ion, then in the electrolyte solution, more will be its specific conductance, because because ions are the ones which is carrying the charge through the solution system. So, if you have more number of ions, the concentration of ions are more, then obviously the specific conductance should increase. Now, what about the mobility? What is the speed of the ions? If the ions are moving very fast, what happens? They are transporting the charge faster. That means the specific conductance should increase. So, the two parameters which is taken to be very important when we are talking about specific conductance kappa, if I have the same solvent system, I do the same experiment held at the same temperature, then it is going to be depending on the type of solute you are using. The type of solute, which is the electrolyte, in which is now dissolved in whatever solvent you are taking. Let us say you are taking water. Then once you have dissolved that, what is the concentration? How much of the ions are in the solution from available from the solute? Obviously, that will depend on the type of solute you are using. So, the number of ions which is generated from the solute, if the number of ions are higher, the specific conductance will be higher, the kappa value will be higher. Now, if these ions, when we are talking about, in the last class we have talked about how the electrode potential is developed, how a cell is charge is transferred, we have done that from very basic. So, I am not going to visit that again. you have to remember that you have a system where you have external circuit completed by battery, and you have 2 electrode system dipped in the solvent. This solvent is an electrolyte solution. So, the velocity at which the ions are moving, if they are moving very fast, then obviously they are going to carry the charge faster, and that is again going to increase the specific conductance. So, what are the factors which is going to affect the mobilities of the ion? On what parameters does the mobility of ion depend on? That we are going to look into in today's class. And what is the another question is the number of ions which is generated. So, what determines the number of ions which is going to be generated in the solution? So, this is one parameter which we are going to look into. What type of classifications we have, or what type of distinguishing parameters we have for a solute to give you a increased number of ions, and hence increased value of kappa, or increased mobility of ions. So, having increased value of kappa. So, these 2 parameters we are going to look into, and this we are talking in terms of the specific conductance or conductivity of an electrolyte solution. Another term which I said is going to be important for our discussion in the coming classes is the molar conductance, which is usually represented by lambda. You will see the resemblance or the similarity which we have with kappa and specific conductance, that is with the molar conductance lambda. You see what are the parameters on which the molar conductance depends on. It is also going to depend on the type of electrolyte, that means the solute system you are using. It is going to be depending on the concentration of the solution, that means number of ions in the solution, and obviously temperature. So, the nature of the electrolyte, what do we understand by when we say the nature of the electrolyte? The conductance of an electrolyte depends on the number of ions present in the solution. Greater the number of ions, greater is the specific conductance or molar conductance. But again, the number of ions which is going to be generated in the solution system which you are dealing with is going to depend on the nature of the solute you are dealing with. Which type of solution is going to give you freely the ions in solution, which are not going to. So, it is going to be indirectly dependent on the nature of the solute you are dissolving. So, the nature of the electrolyte. So, the number of ions, if it is increased, it is going to increase not only the specific conductance, it is going to increase the molar conductance lambda as well. But again, that is going to be determined by the type of electrolyte, nature of the electrolyte we are dealing with. Now, the concentration of the solution. You just see we have taken concentration of the solution. The number of molar conductance of lambda of electrolyte varies with the conductance which we know. If the molar in general the molar conductance of an electrolyte increases, if the molar conductance of a electrolyte increases, it causes with decrease in the concentration or increase in the dilution. Means what you are talking about is more the dilute we make, the molar conductance is going to, this is a general perception. It is, we are going to look into specifics in a while. So, what we are looking into, we have a concentration dependence for this molar conductance. We are talking about molar conductance, we are not talking about specific conductance here, but more or less the parameters and the way they are going to be affected will be similar. So, in this concept what we have, the number of ions in the solution is going to, if the number of ions are more, then you have more molar conductance and also specific conductance, and that is going to be dependent on the type of electrolyte you are using or the solute you are using. Now, with the dependence on concentration, if I have a solute which is of high concentration, then my molar conductance will be lower. This is the general condition which we have. the more you dilute this electrolyte solution, you will have an increase in the molar conductance. And what happens to the temperature parameter? Whether we talk about specific conductance or molar conductance, conductance as such is going to increase when you are increasing the temperature. We have done kinetic theory, we have done the transport property in gaseous system. All of these parameters, from all of these discussions we know that when we are increasing the temperature, we are increasing the kinetic energy of the particles, and if their kinetic energy is increased, means the velocity of the particles are increasing, and if the velocities are increasing, the specific conductance and the molar conductance are going to increase, right. So, the next one we are going to look into is how are these conductivity parameters going to explain the molecular motion in liquids. Okay. So, what do we have when we have an electrolyte system? We have a solute and a solvent, and this solute is dissolved in the solvent, and here we have a the charge carried over along the solution by ions. So, what we are looking into? We are looking into transport of charge by ions. So, all we are discussing is transport properties, right. So, we are talking about transport properties in a liquid system, where you have a electrolyte. Electrolyte is a solid which is dissolved in the solvent, and the charge is transported from one point to the other by ions, which is generated as we dissolve the electrolyte in the solution, whatever be the solvent medium you have chosen. Now, if you have a closer look at this, what happens when what system are we dealing with? We have done discussion with electrolysis cell in the last class. What we have? We have an electrolyte and we have two electrodes, and the distance between the two electrodes, let us say, is L. Okay. So, the potential here, suppose it is phi and phi 1, and the potential here is the phi 2. So, what is happening is you have a potential difference across these two ends, the two electrodes, and the system is connected by to a battery, so that you have the ions flowing and the circuit completed. Okay. So, what we are looking into is the transport of charge by ions, and interpreting transport in terms of what? The amount of charge that is being transported by the ions and the speed with which individual ions move, because if it is going to be how fast or how slow the ions are moving, and that is how easily or how difficult it is to transport the charge. What we will look into? We will look into how the molecules are moving when they move under the electric field in a system where you have a potential gradient. So, potential gradient is going to be applied across the solution system, and this potential gradient is going to accelerate the particles. Across the potential gradient, we have a acceleration of the particle, because if you have two charges, the positive charge is going to move to the negative electrode, and negative charge is going to move to the positive electrode. So, they are driven by the potential difference you have, the potential gradient you have across the solution system. So, this is the accelerating force which is going to have them moving. But again, you have a retarding force, frictional force, because you are in a solution system where you have intermolecular forces, you have the viscosity of the solvent medium to be considered. So, this frictional force is going to try to retard the motion. So, when we have a condition, when the accelerating force, which is the potential gradient, is balancing the frictional retarding force, then the ions or molecules are going to move with a terminal velocity. I hope you remember the Stokes law, how buoyant force and friction force are going to be and gravitational force are balanced, so that they move with a terminal velocity. That means they are going to not further accelerate or decelerate, they will move with a constant speed. That is known as the drift speed. Drift speed is reached only when the force exerted on the ions is balanced by a frictional retarding force existing in the solution system, right. So, before we go into how we are going to be looking into the various movement of ions, how the ions are going to, how much charge is going to be transported at what speed, we are going to go into something basics, very basics, as to what type of electrolyte system we are talking about, because we talked about various parameters which is going to affect the specific conductance and the molar conductance. So, what are the parameters we had discussed? The concentration we had discussed, temperature, we had discussed the nature of the ion, we have discussed the nature of the solvent, nature of the solute and nature of the solvent. Solute is the electrolyte. Okay. So, before we go into that, we will see how the variation of conductivity is existing in terms of the molar conductance. Okay. Variation of molar conductance, that is the lambda with molar concentration. How a particular electrolyte is going to behave with the change in molar concentration is one of the criteria to say distinguish the type of solute system you have or electrolyte system you have. The variation obviously is going to depend on the number of ions in solution and the interaction of the ions between them in the solution medium. Okay. Interaction between the ions are going to be affecting, because if you have intermolecular forces, you have the solvent solute interaction, you have the solute ion interaction, these sort of interactions are going to be there. So, which type of parameters has to be looked into when we are doing a classification of the type of solute you are having, and which type of solute we are calling it as a electrolyte is supposed to have a higher molar conductance, lower molar conductance with the variation of molar concentration of the solute. So, what are the two parameters which is important? It is the number of ions in solution and the interaction of the ions in the solution medium, how they are interacting in between, okay, between each other. So, based on the concentration dependence, the two parameters we have taken, number of ions and the interaction between the ions. The number of ions is obviously going to be more or less dependent on the type of solute you are having. So, based on how the molar conductivity is going to change with the molar concentration of the solute or the electrolyte, we can classify the solute system or electrolyte system into two. One is a strong electrolyte, one is a weak electrolyte. A strong electrolyte will have a weak dependence on the molar concentration. Okay. In strong electrolyte, there is a diagram we are going to see. In a strong electrolyte, we have this molar specific conductance, conductance weakly dependent on the molar concentration. But if you have a weak electrolyte, then you have a strong dependence of the molar conductance lambda on the molar concentration. Obviously, the classification of the electrolyte will depend on what is the solvent system you have employed as well as the solute you are dealing with. Suppose you have here is an example, that suppose you have a lithium chloride. Lithium chloride, if you dissolve, it is a solid, it is an electrolyte. If you dissolve it in water, then it is going to be a very strong electrolyte system. When you dissolve that in propane, then you have a weak electrolyte system. So, solvent medium is also going to be very important when you are talking about it. Okay. So, what you have here, the concentration dependence, you just see what is, how is the graph looking for the concentration variation of the molar conductance. Molar conductance is lambda here. The molar conductance of this is a strong electrolyte, you see the values and see the variation. The changes in with concentration is not very drastic, you see. So, since it is a strong electrolyte, the variation of the molar conductance is not very drastic, but for a weak electrolyte, as we have seen, for a weak electrolyte, the variation with concentration is going to be quite drastic. So, a weak electrolyte is normal at concentrations close to 0, you have a moderate value, but it falls sharply to low values as the concentration increases. You see, this is the increasing side. So, it is going to be somewhere here at near 0 concentration, and it is going to fall drastically as you keep increasing the concentration. So, what you have here, one strong electrolyte is having a molar specific conductance very strongly dependent, very weakly dependent on the concentration variation. You see the concentration variation you have, and there is not very much drastic change in the values, though there is a slight decrease as you increase the concentration. I have told you that if you the more the dilute you have, generally the molar conductivity is going to increase. So, if you are going towards this side, that means you are increasing the dilution. Towards the increased dilution, the value of the molar conductance increases, but there is no very drastic variation with concentration change for a strong electrolyte. This is a KCl is the classic example of a strong electrolyte, and acetic acid is a classic example of a weak electrolyte, where you have a sharp fall in the conductance, molar conductivity or molar conductance as you increase the concentration. While it is going to have moderately appreciable value at concentrations almost towards the 0. So, when you have a strong electrolyte, what is the characteristics of a strong electrolyte? For a strong electrolyte, it is virtually fully ionized in solution. Examples are ionic solids, strong acids and bases. The concentration of the ion in the solution is proportional to the concentration of electrolyte added. If you have a solute added, or a solute which is going to be completely dissociated, so if there is them completely dissociated, obviously then the concentration of the ions should be the concentration of the solute or electrolyte which you are using. According to the observation of how the lambda value or the specific the molar conductance varies with concentration, Kohlrausch's did various experiments he did, a number of experiments he did. According to Kohlrausch's law, the molar conductivity of a strong electrolyte varies linearly with the square root of the concentration, that is the molar concentration. So, this is the expression of Kohlrausch's law. Okay. What does it say? It is the strong electrolyte, the molar conductance at any concentration is going to be proportional to the linearly dependent on the concentration under root of square root of the concentration in molar units, molar concentration. See, this is an expression of y equal to mx plus c. It is instead of a plus we have a minus, that means it is going to be a decreasing plot. Okay, slope is going to be negative. But if you see, then mx is, this is going to be the m and this is going to be x. That means C is the concentration which is varied, and you have a change in the specific or molar conductance values, and this is the constant for a particular solute, for a particular solvent system. So, what happens if you look at this expression very closely, you will see as the concentration is approaching 0, as we go into having more and more dilute solution and the concentration approaches 0, then the specific conductance will be tending towards the conductance molar conductance at infinite dilution. That is what I have written here. So, the molar conductance is going to be proportional to the square root of the concentration at low concentration, and as C is approaching 0, the concentration is approaching 0, the molar conductance at that concentration is going to approach the molar conductance at infinite dilution or towards 0 concentration. Here you see, this is the molar conductance of the electrolyte at infinite dilution, that is also known as limiting molar conductivity. The K is a constant, and this can be evaluated if you plot lambda versus under root of C, and from the slope you can find out, and this depends on the stoichiometry of the electrolyte, and that is it is if you have type 1 or type 2 type of electrolyte, then it is going to be depend on the stoichiometry of the electrolyte. I am going to discuss this in some time, what is Ma and what is M2A. This is these are two types of, you have 1,1 electrolyte, 1,2 electrolyte. This is 1,1 electrolyte, Ma is 1,1 electrolyte, and M2A is 1,2 electrolyte. So, depending on the number of stoichiometric ions generated in the solution, K will be affected by that, and not per se on the specific identity of the ions. And if you plot the molar conductance with the concentration under root of concentration, then you see for a strong electrolyte, this is the variation you have, and to find out what will be the concentration, what will be the value of molar conductance when C approaches 0, you can extrapolate this value. If extrapolate this value, you can get the limiting value of the molar conductance. So, for a strong electrolyte, the linear variation of molar conductance with under root C molar concentration is going to be, the variation is going to be linear with a negative slope, and it can be extrapolated to values approaching 0 concentration, which is infinite dilution. From there, if you have the intercept, you can have the values of the limiting molar conductance. Okay. We take up the weak electrolytes in the next class. Thank you.